Wait a minute. Oh, hello. All right, welcome back to Monty's Python Show. In today's tutorial, we will be exploring the concept of composition, and we'll be contrasting that against the concept of inheritance when creating Python classes. Let's talk a little bit about the differences between inheritance and composition. So far, the videos in this series have focused on expanding on the concept of inheritance. And inheritance is relationships between classes that are explicit. In other words, they are actually coded in as classes inheriting attributes and methods from another class. And when you think about inheritance, the type of relationship between classes is what's known as an is-a type relationship. So for example, think of a circle. A circle is a shape. A square is a shape. And so you could create classes that define attributes and methods of those things, and it would make sense that the parent class would be shape, and circle and square might be subclasses of that parent class. So in general, inheritance promotes efficiency, allows you to reuse your code from classes already created, and you can alter the behavior of multiple classes in an ancestry line with relatively few changes. So inheritance gives you leverage in your code. You can change the behavior of your program with very few keystrokes and very few code changes. But having that leverage makes it more likely to create conflicts and break your code unexpectedly. So when you have situations of multiple inheritance and common ancestors, when you make a change somewhere in that family tree, it affects all of the classes downstream from that class and can often break your code or create a conflict that Python can't resolve. As we saw in our last video, we talked about the diamond problem. By contrast, composition is a way of organizing classes where you create classes that take on attributes and methods of another class by actually accepting a class as an attribute to another class. So in composition, we think of the relationship as a has-a relationship with another class. So for example, you might think of the example we're going to go through today, which is a car has an engine, and it might have a gas engine or it might have an electric motor. So that type of setup lends itself to a compositional approach, as we'll see. So composed classes are modular and encapsulated, making them easier to maintain and adapt, and it makes it harder for you to break your code by changing any one class. So if we go back to the example that we did several videos ago where we created classes of shapes. Looking at this code here, you can see that we have inheritance structure because the circle inherits attributes and methods from the shape superclass, as does square. So we could rewrite this code in a compositional way. So if you notice in this code, none of the classes have any explicit inheritance. However, if you notice down here where we have created objects of the different classes, for example, we create object C, which is a shape, but we've passed the circle class actually as an argument in creation. And so therefore, shape C takes on the attributes and methods that are included in the circle class. And likewise, we've created an object of the shape class called S, and S takes on the attributes and methods of the square class because we've passed it as an argument in its instantiation. So let's talk about when to use inheritance versus when to use composition. This is sort of a general rule of thumb. If the way you are structuring your classes is based on a is-a type relationship, like circle, square, those both are is-a type relationship with shape, then it makes sense to use inheritance. If you have a has-a type relationship, then use composition. So in the example previously, shapes, circles, and squares, it's an is-a type relationship. It makes more sense to use inheritance. Okay, so let's go ahead and start our first example here. So I'm coding inside of Jupyter Lab using the anaconda.cloud. But whichever development environment you prefer will work just fine for this exercise. So we're going to create 3 separate classes, and we're going to create a compositional class structure. So we're not going to have any inheritance. Let's start with our first class called car. And let's go ahead and create a constructor method for our car class. And let's assume that when we create an instance of the car class, the user is going to pass in a particular type TYP, which is actually going to be itself a class object. And let's define self.type to be equal to type. And we're going to define a regular method called drive. Okay, and the drive method is only going to return a formatted string that says driving, and then we're going to return this variable self.type._drive. And it will become apparent what that is in just a moment, but we're going to define an _drive method in each of our gas motor and electric motor classes. Okay, so that's it for our car class. So now we assume that we can have a car, but the car can either have a gas motor or have an electric motor. So let's define classes for each of those. Our first class will be gas motor. Notice no inheritance. And I'm going to define the _drive method. And the drive method will simply return a string saying this V8 is roaring like a lion. Those of you who enjoy the sound of a big V8 combustion engine will appreciate that. And that's it for our gas motor class. Now let's create our electric motor class. Again, no inheritance. And this will return the string, this EV is so quiet pedestrians won't hear you coming. And actually I need to change my outer quotes to be a double quote if I'm going to write it this way, because I've got the apostrophe inside. So the electric motor _drive method just returns that string. This EV is so quiet, pedestrians won't hear you coming. Okay. So let's go ahead and create some instances of these classes. So let's create one called Guzzler. And it's going to be an instance of the car class, and we're going to pass the type in, which is going to be one of our two classes. So Guzzler is going to be a gas motor type. Okay? And let's also create the secret polluter. It's also a car, but it has an electric motor. So here's that language, that relational language that you should remember from the initial discussion, when to use composition versus inheritance. Secret polluter is a car that has a electric motor, not is an electric motor. So it makes sense for us to be using composition here. All right, so let's go ahead and print Guzzler .drive. That will call the drive method from the car class. And let's print secret polluter .drive and see what we get. Oh, we get an error. Let's see, car takes no arguments. That's not true. My init method. There we go. I had an error in my init method there. I was missing the second two underscores. Okay, so you can see that we created two separate objects, and when we call the drive method of the car class, in the case of Guzzler, it prints driving, this V8 is roaring like a lion, which came from the gas motor. class, and the EV prints, this EV is so quiet pedestrians won't hear you coming, which comes from the electric motor class. So you can see that this works very similarly. It's as if we had inheritance in here, but the way that we made the attributes and methods of each of these quote-unquote subclasses available to car was by passing them as arguments directly in the instantiation of the car classes. Okay, so let's just review what we've done so far. So we think we have a good candidate for composition because we've said that if you have relationships between classes that fit a has-a type relationship, then it makes sense to use composition. So in our case, we're working with different types of cars and cars that have different engines. So for example, one car may have a gas engine while another car may have an electric motor. So composition makes sense in this case. Let's take a closer look at the code that we've written to make sure we understand what's happening. So the first thing to point out is there's no inheritance. None of these classes inherit from any other class. But it's clear that the different objects we've created, guzzler and secret polluter, have access to more than one class. So guzzler, for example, is an object of the car class, but it clearly has access to the underscore drive method that's defined inside of gas motor. So how is that happening? So key number one is when we created the constructor method for the car class, we defined that it would have a type argument passed to it. And type is actually going to be one of our classes. So in the case of guzzler, we passed gas motor as the type argument. And in the case of the secret polluter object, we passed electric motor as the type argument. So that sets up Python to be able to know which class to derive the appropriate attributes and methods for the particular objects. So for example, when we invoke the drive method here on the guzzler object, Python knows to access the underscore drive method here because we specified right here. So this is sort of a key difference between composition and inheritance. Notice we're not accessing self._drive. That wouldn't give Python enough information to know which method to use. But self.type._drive lets Python know that the object that was passed as the argument type is the specific object self that we're going to invoke the underscore drive method of. So in the case of guzzler.drive, you can think of self.type to be the equivalent of guzzler. So this is like saying guzzler._drive when it's invoked by the guzzler object. Similarly, when we created secret polluter, in that case, type is set to the electric motor class. So when we invoke the drive method, in that case, self.type is actually equal to guzzler. So it knows to come down to the electric motor class and access that form of the underscore drive method. Okay, I wanted to just jump back into this section real quick and correct something that I said a moment ago. I equated the self.type prefix here to be the equivalent of guzzler in the case of where we invoke the drive method on the guzzler object, and the equivalent of secret polluter in the case of that object. That is not true. What self.type is referring to is when we invoke drive on the guzzler object, self.type is itself taking on the value of gas motor. And in the case of secret polluter, self.type is equivalent to the electric motor.class. So for example, this would be the same as writing gas motor dot underscore drive. So it's calling the method of each of those classes, not applying it to a specific instance of the class. Okay, so let's go back to our code and let's add some things to it. So here's the idea. Suppose we are creating these classes for a game, and the game involves driving cars. And the player can select a car with different types of engines, and maybe there's many different classes. You may select different cars with different engines, different suspension, different wheels, all different types of things, and the cars will perform differently depending on all of those selections. And if you set that game up, or those classes up compositionally, then you will say that the cars that you select will have an engine or have a particular type of suspension, have a particular type of tires. And each one of those cars may perform very differently one from the other in the game, depending on the attributes and methods that you assign inside of those classes for the elements that you ascribe to that particular car. So in our case, we want to just make our code a little bit more realistic so we can kind of see how it works and see what happens. So here's what we're going to change. We're going to build out our gas motor and electric motor classes first to have more attributes and methods. So let's go inside of our gas motor class and let's create some class attributes. Let's suppose that the gas motor option for our cars has a fuel tank, an engine that has a range of 486 miles if fully fueled. And let's suppose that the fuel efficiency of this is 17 miles per gallon. Now let's go ahead and create a constructor method inside of gas motor, because we want to define some other instance variables inside of the gas motor that make it unique. So let's define _init, and let's assume that when you create a car and you pass gas motor as an argument, you're also going to pass the fuel tank situation to it. So how much fuel is in the tank? So for example, you might create a car that has a gas motor, then the tank is 75% full. So you would pass 75 as the argument. So we're going to refer to that variable here as fuel percent, fuel PCT. Okay, so let's go ahead and create those instance attributes. Self.fuel PCT equals fuel PCT. And now we also, so we have a class range that assumes that the tank is full of 486 miles, but given that the fuel percentage might not be 100%, we can use that to create an instance range. So self.range times equals the fuel percent divided by 100. So the the range would be equal to whatever the range was times the fuel percent divided by 100. Okay, so in other words, if you started off with the tank 50% full, your range would actually be 243 miles. Okay, then we want to also define a string method because we're going to use that up in our car class. So let's define _string, passing self as the argument, and we want our string to return the following formatted string. Gas motor, so it's identifying what type of motor, what the current range is, self.range, and what the remaining fuel is. Self.fuel PCT and 0.0f, we'll format it this way. Okay, so now we have a string method. Now we're going to eliminate the _drive method inside of the gas motor class, because if you think about it, the motor doesn't drive, a car drives. So logically, given our composition, a car can have a gas motor, but it's the car that drives, not the gas motor. Okay, so we're going to actually handle driving up in the car class. Okay, so that does it for the gas motor class. Let's beef up our electric motor class a little bit. Let's suppose that the range on a full charge of our electric motor is 320 miles, and the efficiency, the miles per kilowatt hour, mpkWh, is equal to 3.2. Let's also define a constructor method for electric motor. And in this case, instead of fuel percentage, with electric motors and batteries, we think of the state of charge, SOC. So when we create an electric motor object, we will pass the state of charge as an argument. Now let's go ahead and create those variables. Self.soc equals SOC. And similarly, we're going to have an instance range, self.range times equals SOC divided by 100. And lastly, let's define a string method like this. We want this string to return something similar to the gas motor, but a little different. It's going to return electric motor range equals self.range, and SOC equals self.soc, and we'll give it a little formatting. Okay, and let's eliminate the underscore drive method, because again, the electric motor doesn't drive, the car drives. Okay, now clearly we've got to change our drive method up here in the car class, because all it was doing was calling the underscore drive from whatever self.type was, from gas motor or electric motor. So that's not really going to work. And let's suppose that when we invoke our drive method, we want it to assume that the automobile drives a certain number of miles. So we want to pass how many miles it's driving as an argument. And then we want to keep track of the fuel usage and the reduction and the range from having driven. So we want our drive method to drive the car and then return a message about what the current range is. So it's going to update us on the status of our drivetrain, if you will, the gas motor or the electric motor. Okay, so let's go ahead and change our return. Oh, actually, first we need to add the argument miles in our definition of the drive method. So we have define drive self and mile. And so the first thing we want to do is when we drive a certain number of miles is we need to update the range. But we need to update the range for the particular class of motor or propulsion type, the gas motor, the electric motor. So here we're going to update self.type.range. And we're going to decrement that minus equals however many miles we've driven. So if we had a range of 200 miles and we drive 100 miles, we want to update the range attribute of that particular object to 100 miles. Okay? And then we also need to update the fuel percentage or the state of charge. Okay, so we can't do that in the same way for our two engine types. So that was the point of creating the string methods in each of our gas motor and electric motor classes. So we can identify which type of motor or propulsion system we have with this particular instance. Here's how we're going to do that. If gas motor in self type dot string. So this is going to call the string method for self.type. So if we had a gas motor, it would call the string method or invoke the string method of the gas motor type, and that would return this string which has gas motor in it. So if that's true, if it was a gas motor, then this condition would be true. Gas motor would be in that string. So if that is true, then what we want to do is we want to update self.type.fuel percent. Okay, and so the fuel percentage is going to go down by whatever the capacity of a full tank we use. So minus equals, and we're going to decrement that by miles divided by gas motor dot range times 100. Okay, so you see what's happening here is miles is coming from, that's actually going to be an argument to the drive method, so that will get passed. So that's where miles will come from. And we're dividing by gas motor.range, so that's going to access the class attribute here, 486. So in other words, if we drove 48.6, then by definition, we're reducing our fuel percent by 10%. So this would reduce whatever the existing fuel percentage is for that particular object by 10%. And let's just, for now, we'll handle this in the form of an else. Now you could do an elif and then test to see if electric motor was in the string, and then you could use else to possibly raise an exception if there was a different type. But for now, let's just do it this way, else, and we want to update self.type.SOC. That is the relevant attribute for an electric motor type. But the math is going to be the same. SOC minus equals miles divided by electric motor dot range times 100. So now this will look into the electric motor class attribute range, which is here, 320. So for example, if we drove 32 miles, if we had passed 32 as the miles variable, then it would reduce the range by 10%. Now, let's return a string that reads something like this. Drove, and then we're going to print the miles variable that was passed, mi, and then let's add to that self.type._string. So that is going to add the information that is produced by the string method. So it's going to give us an update on our range and the remaining fuel. So we updated those variables here in this if-else structure, and then when it calls the string method here, it should send back those updated values for self.range and self.fuel percentage. In the case of a gas motor, in the case of an electric motor, it would return the range and the state of charge. Okay, so now we need to just change our code down here a little bit. Let's create maybe like a series of drives for our two autos. And we need to also change the creation of the objects. So we need to pass an argument inside of the gas motor and electric motor classes, because if you recall, we created constructor variables that require a fuel percentage or a state of charge to be added. So let's just suppose in both cases, let's suppose we have 50% fuel remaining for our gas motor car, guzzler, and we have 50% state of charge remaining for secret polluter object. Let's just create a loop here for n in range 4. Let's print guzzler.drive, and let's say we're driving just 4 legs of 25 miles each, just so we can see what it does each time. And then let's print secret polluter.drive, also driving 25 miles. All right, and let's see if this runs without error. I'm just going to add at the end of this print statement here a new line character so that it makes it a little easier to read. Okay, so there you can see, so in this loop it drove the guzzler 25 miles. So you can see that it its range is 218 miles. So what's going on there? So when we first created the guzzler object, it had a 50% fuel remaining, so its range was 243, and then we drove 25 miles, so now the range is 25 miles less than that, 218, and you can see that we used 5% of the fuel. And the same for our electric motor car, which is secret polluter. It drove 25 miles, and its range is now down to 135, and state of charge is 42. And so you can see each time it decrements down each of the range and the state of charge. And then you probably create some logic in your game code where you can fill your automobile up with gas, and maybe that costs some money, and you can charge your electric vehicle and so forth. Okay, so that does it for this episode of Monty's Python Show. Hopefully today's video helped you better understand composition, how it's different from inheritance, and helps you create better classes. Until next time, wipe the crumbs out of your beard and Python.